Hello everyone. So now we're going to look at the graphs of a chemical equilibrium. Let us make the example that we were always doing from the previous videos. Let's say, for example, now we have a reaction of A2, and then that is reacting with what? Let's say now it is reacting with 3 moles of B2, and the reaction goes forward. And then now we have 2A, our product. Okay, so now when we deal about the graphs of rate of reaction, so I just want you to pay attention here. So I'm just going to make a difference between two graphs. I will actually tell you what. Let's say, for example, we have a concentration time graph. That means on the right here we have concentration, and on the bottom we have what? We have time. And then now let's say, for example, another graph that we're going to talk about is a rate graph. So the rate graph is a rate, and then there's a time. Okay, so now the reason why I'm talking about concentration. So remember now, a concentration is related to moles. So let's just look at the equation here. You remember the equation of a concentration is actually concentration is number of moles divided by volume. So now you can see concentration is directly proportional to number of moles. So basically this function here, or this graph here of a concentration, will behave the same way as if we had a graph of number of moles. So basically we are hitting two birds with one stone. So a concentration will behave the same way as number of moles. Okay, so now let us look at this, what is happening here. So remember, initially whenever you have a reaction, your reaction start first with what? With reactants. And then when it start with reactants, and then when time goes, it forms what? It forms the product. So there is no reaction that start up at equilibrium. So it must first start with the reactants, and then it becomes product. So that is why I was emphasizing to say initially your reaction is always a forward reaction up until it reaches its equilibrium state. So now let us look at the concentration here of the reactants. So let's say, for example, you will see now A here will have less concentration with B because B has more number of moles. So I'm just going to make let me just make here I'm going to make this will be B because it will have more concentration than A, and then this will be A here. Okay, yeah, and then now, so now look at what is happening. So when we react these two things, so we will use them up, they will start to decrease its concentration, and then now we will form what? Will form the product, which is this one. So now when the reaction goes, it decreases what? It decreases the concentration of boron or B, and it also decreases the concentration of A. So this one we'll call it a B, and this one we'll call it A2. I'm sorry, I don't have a good system. Maybe I would have used different colors, but I don't have a good system to try and explain this. But just pay attention here. So now, when the concentration of these reactants are used, now the concentration of the product is increasing because now we are forming what? We are forming the product. So now remember the product will start at 0, but now it will what? It will start to increase. So that means now that will be a concentration of what? That will be a concentration of a B. Three here is B3. I'm sorry about that. B3. Okay. Okay. So now, remember, we talked about this is just to show you how the concentration increases and how the number of moles decreases. It's just a forward reaction that is happening. Yeah? So now let us look at the rate here. What will happen to the rate? Let's say, for example, you start here with a forward reaction. So now at the forward reaction, your reaction is starting. Your forward reaction is starting. So remember, as the reaction starts, we have a lot of moles here. Yeah? A lot of moles of A and also a lot of moles of B. But when the system reacts, it will what? It will decrease its moles. So when the moles start to decrease, that means what? Your forward reaction will also start to slow down. because now the products are being formed. That means the reaction is coming to an end, or maybe it's coming to an equilibrium. So now your rate of reaction will start being fast, because now you have number of moles of argon reacting with a number of moles of B, so that it can form the product. So it's a lot of number of moles reacting. So your rate when it start faster, but then as it goes, remember the concentration and of the reactant starts to decrease, and then the forward reaction starts to decrease. Okay, this will be the forward reaction. And then now what will happen to the reverse reaction? So remember now, as soon as we start reacting the reactant, the product will also start to form. That means the reverse reaction will also grow now and start to form. Okay, so now it means now when we form when we react the reactants, the product is starting to come up, and then when the product start to be produced, this product will also want to form to form the reactants. So it will be a reaction that is back and forth like that. So up until what happens, up until we both reach the equilibrium. So now at the equilibrium state is whereby now the rate of a forward reaction, it will be equal to the rate of reverse reaction. So these lines here of the reaction of forward and reverse, they will be what? They will be parallel. Okay, and then now here also, when the reaction is reaching equilibrium, that means now all the rates will be, the concentration of everything will stay stable. So the concentration of boron of A and B will stay stable, and also the concentration of the product will stay stable. Okay, so now let us see. Remember, we said when we disturb the reaction, the Latalia's principle, it says now the reaction will act in a way that it wants to oppose the disturbance. So we can only disturb the reaction when we disturb what? Let me just tell you these three factors. When we disturb what? The temperature, concentration, and pressure. So basically, when we disturb the pressure, the temperature, or the concentration of one element in a reaction, that means now we have disturbed what? We have disturbed our chemical reaction, which is at equilibrium. And then now this chemical reaction at equilibrium, what it will do, it will react in a way that it wants to oppose this change of whatever stuff that you have changed. Yeah? So now let's say, for example, okay, so now here on our graph, this graph, it represents what exactly is happening. Yeah, okay. So firstly, let's now check if ever we do what? We increase the concentration of A. So if we increase the concentration of A, let's just make an example. On your graph, the graph of A will just move up a little bit. This shows now the concentration of A is what? Is increased. So this one shows the concentration of A was increased. So even if they say the number of moles were increased, so remember we said concentration is related to number of moles, because they are what? They are directly proportional. So the concentration of argon will increase. And then what will the system do? What Le Chatelier says that, okay, if you increase the concentration of A, Le Chatelier's principle says it will favor what? It will favor what? The forward reaction, because it will want to make A be a reactant. Because if you increase the concentration of A, the system will want to decrease the concentration of A. So you decrease something as concentrations if it's a reactant. So remember, if it's a reactant, it starts to react, and then its concentration will do what? Will decrease, and then it will increase the concentration of the product. So that means now if you increase the concentration of A, a forward reaction will be favored, because this forward reaction will oppose that increase in concentration, because if forward reaction is favored, the concentration of A and B will be decreased, so the system will react in a different way. So now let's look at what will happen to the concentration of the reactants and the product. So remember, we said now when you increase the concentration of A, that means a forward reaction will be favored, because the system will try to decrease the concentration of that. So okay, so now if the forward reaction is favored, that means the A and B will be used up, will react to form B. So now you go to A is starting to react, that means it decreases, and then B, it also reacting, that means it decreases, and then see what happens to the product. The product will do what, will increase, because now its concentration will increase when the reaction is going forward. So now the product will do what, will increase. Okay, and then up until there, the new equilibrium is reached. Okay, I hope that makes sense. So let's now look at what will happen to the rate reaction. So remember now, if you increase the concentration of A, that means, oh, you are making to this forward reaction to have more more concentration, more number of moles. So more number of moles, that means the faster the what, the faster the reaction. So now the forward reaction will be what, will be increased, because you are increasing the concentration of what, of the reactants. If you increase the concentration of reactants, that means what, you are increasing the rate of what, of the forward reactions. So when you increase the rate of the forward reaction, so now in your reaction diagram, your rate of what, of your forward reaction, it will increase, it will spike up like this, and then when it starts to increase, it will cool down a little bit, but it will stop where, at a little bit higher place where by than initial reaction started. Okay, so now if you increase the concentration, that means you're increasing the rate of the forward reaction, so that means it will spike up, the forward reaction will spike up, and then it will decrease now. But when it decreases now, it decreases a little bit higher than initial state of rate. So now when this increases, the reverse reaction will also wants to catch up with that one, and then it forms what, until it reaches equilibrium again. Okay, so that is how the increase in concentration affects the rate of reaction diagram, and it also affects the concentration diagram. Okay, so now let us make another example to say now, okay, let's say now we decrease what, we decrease the concentration of what, let's decrease the concentration of B. Let's say, for example, we decrease the concentration of B. Okay, so what will happen? Okay, on our graph, we will see that, okay, the concentration of B will do what? It will start to decrease. So it decrease a little bit, is what, is a concentration of what, of B. So, but what will happen to the system? So remember, if you decrease the concentration of B, the system will react in a way that does what? It increases the concentration of B. So it opposes the disturbance. So now, it means what? It means now the reverse reaction will be favored, because now if the reaction wants to increase the concentration of this, it must make it a product. If it wants to increase its concentration, it must be a product. So that means now the reverse reaction will be favored. Okay, so now if we favor the reverse reaction, what will happen? So now if we favor the reverse reaction, now this what? This product of ours is starting to be a reactant. So if it's a reactant, it will what? It will start to decrease. So now our product here, it will start to do what? It will start to decrease. But what will happen to our reactants? So our reactants now are now our product. So that means now its concentration will do what? Will increase. Now the B will increase, and then now C will increase up until the new equilibrium state is reached. Okay. Okay, so now what will happen to our rate of reaction diagram? Okay, so now remember, if you decrease the concentration of the reactants, that means what? The forward reaction, it will be what? It will be decreased. You see now, the forward reaction, it will be decreased. So what will happen? That means now the reverse reaction will be more faster than what? The forward reaction, because you decreased what? The concentration of what? Of you decrease the concentration of the forward reaction. So now the forward reaction, it will do what? It will drop down. That means this forward reaction, it will go, it will spike down. Yeah, but what will happen? The concentration of a reverse reaction will be a little bit higher than the concentration of the forward reaction, because what? We decreased the concentration of the reactants. So what will happen is that when this forward reaction starts to reach equilibrium again like this, so the reverse reaction will just come up and want to follow. But the reverse reaction will be what? Will be a little bit faster than the forward reaction. Now you see the forward reaction is below, but the reverse reaction is above. Okay. Okay, I hope that makes sense. If you don't understand, please just pause and go back to it again. Okay, so now I'm just gonna move to see if ever what will happen when we change the temperature and when we change the pressure. Okay, so I'm just gonna remove this graph from here. Okay, let me just remove from here. But here initially is how our graph is reacting initially. And then let me just here and here. Okay, so now let me just say, for example, when you increase what? When you increase a temperature, a concentration, or a pressure, that means you are increasing what? You will increase the rate of reaction. So every time when you increase temperature and pressure, your rate of reaction will always increase. So now when you decrease the following, your rate of reaction will do what? Will decrease. So that is just what you have to know. When you increase temperature, concentration, or pressure, the rate of reaction will do what? Will increase. But when you decrease them, your rate of reaction will decrease. Okay. So now let's look at what? Let's look at a temperature. Okay. How does the temperature affect what? Our equilibrium state of a concentration or of a reaction. Okay. So now if we talk about a temperature, okay, most of the time they will have to give you an indication to say now what is the forward reaction doing. So they will just indicate it by a change in H. Change in H. If change in H is less than 0, okay, that means what? That means now the forward reaction is exothermic. So remember, changing H less than 0 is standing for exothermic. Okay. So if you are given this condition on your reaction, that means this condition is for a forward reaction. Always remember your reaction start with what? With reactants, and then it forms a product before it reaches equilibrium. So this condition here is for what? Is for a forward reaction. So now that means what? Our forward reaction is what? Is exothermic. Ne? Is exothermic, and exothermic means what? Means hot. Ne? Exothermic, it means hot. Okay. It means hot. Okay. And then now our reverse reaction will be what? Our reverse reaction will be endothermic. It will be endothermic. And then endothermic, it means what? It means cold. It means cold. Okay. I hope that makes sense. Okay. So now let's look what is happening. So let's say, for example, we want to increase the temperature of the reaction. So what will happen? So if we increase the temperature, what will the system do? The system will want to act in a way that it decreases the temperature of the system. So remember, if you increase the temperature, the system will want to make the temperature to be what? To decrease. So the temperature decrease is what? It favors a endothermic reaction, because now if you increase the temperature, the reaction will want it to make the reaction to be cold, which means now endothermic will be favored. Okay, so now an increase in temperature will favor what? A reverse reaction, because increase in temperature favors a cold reaction, which is now endothermic. So what will happen to our graph? So now remember here, when you increase the temperature, what will happen is that you are not increasing a concentration or a number of moles of anything, but now you are increasing the temperature. So but this temperature will do what? Will favor the reaction that will decrease the temperature, which is a reverse reaction. So when you favor the reverse reaction, what will happen? That means your reactants will be what? Will be now your product here. So that means this product here, it will be used up, and then this one will be formed. So that means what? When is it equilibrium? The concentration of what? Of your product, it will decrease. And then what will happen to the concentration of this reactants here? It will now what? It will now increase, because reverse reaction is favored. Okay, because the reverse reaction is favored. Okay. Okay, so now this one, it will what? It will reach its new equilibrium state. Okay, I hope that makes sense. Okay. Okay, so now let us look at the rate of reaction. So now here on the rate of reaction, we said now when we increase everything here, what will happen? The reaction will do what? Will increase. But when we decrease everything here, the reaction will decrease. So now let's see what happens now. If we increase the temperature here, but now what? the reverse reaction is what is favored. Now, do you see now the rate of forward reaction? It will be the one that increases because the the reverse reaction is favored. So when you, okay, let me just make a highlight here. When you increase the temperature and pressure, both your forward and reverse reaction will both increase. They will both spike up, no? But they won't spike with the same amount, because now we will check at which reaction is favored. So in this case, the reverse reaction is favored. That means it will increase more. So now we go to here to the reverse reaction. Your reverse reaction will do what? Will increase more. But now what will happen to the forward reaction? The forward reaction will also increase. But now what happens is that because the reverse reaction is favored, what? The reverse reaction is increased more, but also the forward reaction is increased. And then now the reverse reaction will start to want to reach its new equilibrium state, and then the forward reaction will do the same and reach its new equilibrium state. Okay, I hope you understand that. If you don't understand, please just try to go to take the video back and try to understand what I'm trying to say. Okay, so now let me just make another example. Now this example will be what? A decrease in temperature. Let's say now we decrease the temperature of this reaction here. So what will happen if we decrease the temperature of all of this reaction? The system will want to increase the temperature of the reaction. So if you decrease the temperature, so the system will favor what? The exothermic reaction, because exo, it means hot. So now this forward reaction will be favored. Yeah. So now when you favor the forward reaction, that means now your reactants are reactants and then your products are products. So now what will happen? These reactants will react up, and then the products will increase. So you guys just go to your A and B. These ones will decrease, and then this one will decrease. But what will happen to the product? The product will do what? Will increase up until the new equilibrium is reached. Okay, I just hope that makes sense. So pay attention now. When you increase the temperature, nothing is spiking up. It's just the favoring of reaction, and then everything react in a way that the reaction favors act. Okay. So now what will happen? So remember, I said when we decrease what? The temperature, what happens? We do what? The rate of reaction will decrease, but decreasing the temperature favors which reaction? It will favor what? The forward reaction. That means the forward reaction will have what? A faster rate than the reverse reaction. But now the condition is that when you decrease the temperature or concentration or pressure, your reaction will decrease. So now your forward reaction will decrease, but it will be higher than what? Your reverse reaction, because your forward reaction is favored. So now also your reverse reaction will decrease. It will decrease more because of what? Because of that. I'm sorry about that. Let me just erase here. Okay. So basically, a forward reaction is this one. It increases first and it goes there. So now what I'm saying is that, okay, so because we are decreasing the temperature, and when you decrease the temperature, the forward reaction is favored. That means when you favor the forward reaction, that means the forward reaction will be faster. But what happens is that you decrease the temperature. So the decrease in temperature, it decreases the rate. So now the rate of what? Of forward, it will decrease. But what will happen? The rate of reverse, it will decrease more, because what? The forward reaction, it must have a faster reaction. So this one, it will decrease more, because we are favoring the forward reaction. You understand? And then now this one will start to go down and reach equilibrium, new equilibrium, and then the forward reaction will come and reach its new equilibrium. Okay, I just hope that makes sense. I hope it does make sense. Okay, so now lastly, let us look at how the pressure affects the equilibrium concentration, okay, or the equilibrium state. Okay. Okay. So now let us say now, okay, we have started our reaction now, but now what happens is that we increase the pressure of the system. So what happens when you increase the pressure of the system? That means you are decreasing the volume of the system. Let's say, for example, we have a container here, and then this container, it has 1 mole of argon, and then it has 3 moles of B. Okay, so now when you decrease this volume, the volume will do what? Will decrease, and then this one, they will compress together. They compress together, and then that means when they compress together, the reaction will start to be faster. Okay, so what happens is that the concentration of everything, remember when you decrease the volume, the concentration of everything, it will increase. It will be more concentration. So now on your concentration and number of moles graph, everything will spike up. And the increase in pressure will increase the concentration of everything a little bit. Everything a little bit. Okay. And then now when you increase the concentration of the system, what will the system do? The system will act in a way that it wants to oppose the concentration. So now let's look at here. Okay, let's look at here. Do you see now on our initial reaction, on our reactants, we have a 1 mole here plus 3 moles. That means it will be 4 moles. But now at our product, it will be 2 moles. Okay. So now when you increase the pressure it does what? It wants to favor the temperature whereby the pressure will be decreased. So you see now here on this side we have more of what? More of gas, which is 4 moles. So if we want to decrease the pressure, we want to do what? If we increase the pressure, we want to decrease what? Decrease that moles. So that means now you will move from 4 moles to what? To 2 moles. That means the forward reaction will be favored, because the Le Chatelier will always wants to reverse the reaction. So let me just try to repeat myself here. What I'm saying is that when you increase the pressure, the concentration of everything in the reaction will increase. But now when you increase the pressure, the system will want to decrease the pressure of the system. So now let's look at the example. Here on our reactants, we have what? A more concentration, because we have like 4 moles, and then on our products, we have 2 moles. So here on more concentration, that means there's more pressure, and here on this less concentration, there's less pressure. So if we increase the pressure, the system will want to what? Will want to decrease the pressure. So it will favor a forward reaction, because you can see now this one, it will move in a way that it will have what? A less gases, less concentration. I hope that makes sense. Okay. So now how will the system react? Oh, it favors the forward reaction. That means now your reactants A and B will start to decrease. It will start to decrease, but what will happen to the product? The product will now increase up until a new equilibrium is reached. Okay. Okay. So now what will happen to our rate of reaction? So now the rate of reaction, remember the rate of reaction, what it does, if ever you increase the pressure, it increases the reaction. Yeah? But now pay attention that the forward reaction increases and the reverse reaction increases. But now, because we have favored the forward reaction, that means the forward reaction will increase more, and then more than the reverse reaction. And then the forward reaction will start to wants to stabilize, and the reverse will start to reach that state there. Okay, I hope that makes sense. Let us also look at when we decrease what? When we decrease the pressure of this system. When we decrease the pressure, so remember, when we decrease the pressure, oh, that means the concentration of everything will do what? Will start to decrease. So we spike everything down here on the concentration. Okay, but now a decrease in pressure will favor what? Will favor a system will want to what? To increase the pressure of the system. So remember, the number of concentration on your left here is 4, and this one is 2. So that means what? It will favor the what? The one that has more number of moles. That means it's going to be what? The reverse reaction will be favored. So the reverse reaction will be favored, because when you decrease the pressure, the system will want to increase the pressure by favoring the side that has a more number of moles. I hope that makes sense. So now when this reverse reaction is favored, that means now your product here will start to decrease, because we are moving in the reverse reaction, it will start to decrease. But what will happen to the reactants? They will increase, because they are now the products. Okay. Okay, that is what will happen here on your concentration and number of moles diagram. But now what will happen to your rate of reaction? Remember, I said if ever you increase the pressure or you decrease the pressure or temperature, your reaction will decrease if you decrease. So that means now, okay, both our reactions will decrease. Remember, when you use temperature and pressure, both the reaction decreases or increases the rate of reactions. Okay, so now what will happen if we decrease the pressure of the system? That means now we are favoring the reverse reaction. That means the reverse reaction will do what? Will be faster than what? Will be faster than the forward reaction. But now remember, we decreased, so now this one, it will decrease. But because we favored the reverse reaction, it will be faster than the forward reaction. That means the forward reaction, it is the one that will decrease more. When it decreases more, and then it will start to once to reach its equilibrium state, and then the reverse reaction, it will want to follow up here. Okay, yes, I hope everything makes sense. Just make sure you go back and forth with the video. I will just make question papers. I will just go through the question papers to see what you actually mean about everything that I've just said here when you apply it through the questions. Thank you very much.